Today we're going to look at a differentiation technique, and it's one that we're going to use for finding the derivative of composite functions. So taking a look at this function here, y equals 2x squared minus 5 all squared. One approach to this would be to expand the brackets first of all. In fact, you've dealt with functions of this form. So we could expand the brackets. We would get minus 20x squared plus 25. If you're unhappy going straight to this, of course you could draw out your double brackets and expand and simplify. From here we could find the derivative just using the power rule that we've been practicing so far. So I'm multiplying by the power and reducing the power by 1 each time. 40x, and that is a constant, so it becomes 0. Okay, we have found the derivative. Let's take a look at a second technique for finding the derivative of a function of this form. And here we're going to go back to this idea that this is a composite function. It's one function inside another function. And this inside function is what's inside the brackets, 2x squared minus 5. So this function is being squared. Okay, so that's our this is our inside function. So y as a function of u. So we've got u as a function of x. If we want to write y as a function of u, it would be y equals u squared, because we're squaring u. Next, we're going to find dy by du. We're going to differentiate this with respect to u. So I will get 2u, multiply by the power, reduce by 1. And we're also going to find du by dx. So I'm going to go up to this and differentiate this with respect to x now. So multiply by the power, reduce the power by 1. Okay, so we found this, yes, and this, and then the product of dy by du and du by dx in terms of x. So I'm multiplying these two together. Okay, so what happens when we find dy by du times du by dx? Well, I would get 8ux. But it says in terms of x, which means that I shouldn't have any u's in. So what I'll do now is I will substitute this back in there. So I'll do 8 times this times x. I might move the x to the front and then put u in afterwards just to make it a little bit tidier. And lastly, I'm going to expand my brackets. So I'll get 16x cubed minus 40x. Okay, what do we notice? We notice that by multiplying dy by du with du by dx, we get the same as what we found with dy by dx. Clearly this method took us a lot longer. Let's take a look at one more example. You might want to try this on your own, pause the video, work through it, and then skip ahead. So once again, expanding the function, I will get x to the power of 6 minus 2x cubed plus 1, and then finding dy by dx. I'll multiply by the power, reduce by 1, and there's my derivative. Okay, we're going to do the same process as before. We're going to think of an inside function. This is the first thing that's happening to x. We're doing x cubed minus 1. And then the outside function, the second function, is squaring. So u in terms of x is x cubed minus 1. And we can think of y as being u squared. This squared is the same as this. Okay, we're going to find dy by du. We're going to multiply it with du by dx. And we're going to write this all in terms of x at the end. So let's start dy by du equals 2u. Du by dx, I'm differentiating this here, is 3x squared, and then I want to multiply them. So dy by du times du by dx equals 2u multiplied by 3x squared. and then we're just going to simplify this. We're going to substitute back in this expression for u. Okay, so I've got 6x squared multiplied by u, and u is x cubed minus 1. So we can expand 6x to the power of 5 minus 6x squared, which is once again the same as dy by dx. This seems like a bit of a waste of time, really, when we managed to find dy by dx so much quicker just by expanding and differentiating. So why would we bother to look at this? Obviously, if we have a different power here, if our outside function is not just squaring but maybe to the power of 8, for example, expanding this would become a much more onerous task, and perhaps this would become easier. Or maybe instead of our outside function being raising to a positive integer power, it's raising to a fractional power or a negative power. Or, as we'll move on to look at other types of functions, maybe it's a whole different type of function. Maybe our outside function is a trigonometric function or something like that, something that's going to make this a lot more complicated. So we've used this method, the chain rule, on examples that we probably wouldn't be best off using it for. We'd actually be best off doing this. This is the best method for this question. But we're going to take a look at a couple of examples now where the chain rule is really our best option. Okay, so this is our chain rule for composite functions. To find the derivative, we are finding dy by du and multiplying it by du by dx, where u is our inside function. One thing to be clear is we're not thinking of this as fractions and just cancelling out the du's. That is not a correct understanding of what dy by du actually means. It is, however, a very useful way of remembering it because it looks right from our fraction work in the middle school. It looks right that it would cancel. It's not what's happening, but it's a good way of remembering it. Not that you need to remember this, this is in your formula guide. Okay, let's look at this now for a couple of examples that are not as straightforward as the one above. So if we were to try and rearrange and expand this, we would think of this as 3x minus 5 to the power of a half. Now expanding that is much more complicated, and then finding a derivative is a bit trickier. So we're going to use our chain rule here. And we start by identifying our inside function, which is what is in this case in the parentheses. It's always quite nice when one function is in parentheses because it's clear that that is your inside function. So that is my inside function. I'm just going to write down the formula we're using. Dy by dx equals dy by du times du by dx. Let's move this out of the way, we'll come back to this in a minute. Okay, so I need to find dy by du, I need to find du by dx. Let's just write y in terms of u. If u is 3x minus 5, I can think of y as u to the power of a half. So now I can find dy by du, multiply by the power, reduce the power by 1. I can find du by dx, which would be 3. And then to find dy by dx, I would multiply dy by du, a half, u to the power of a negative a half. I'm going to multiply it with 3. Okay, I'm going to do a little bit of tidying up now. So this is 3 over 2 root u. Okay, I've thought about the negative and the fraction. The u has moved to the denominator and the fraction is our root. And then finally I'm going to substitute this in because really I want it in terms of x. So dy by dx is 3 over 2 root 3x minus 5. Okay, not a question we could have attempted at the moment in any other way. Okay, so I think part B is really the same idea. We would think about this as 2x plus 3 and the power is negative 1, and clearly this is our inside function. So rather than going through this example, you can check your answer on the class notes. Let's take a look at a slightly different approach to the chain rule, which you may prefer. Let's put this up here. Okay, just rule that off. Right, so another way of thinking about this is thinking about inside functions and outside functions. So our function was 3x minus 5 to the power of a half. So our inside function is this here. That is the inside. The outside function is square rooting it, or raising it to the power of a half. So what we can think about is the derivative of the inside function multiplied by the derivative of the outside function. Okay, so the derivative of the inside function is 3x minus 5. So if we find the derivative of this, it would just be 3. That is the easy part. Next, the derivative of the outside function. If we have something to the power of a half, we would use our power rule. We would multiply by the power, and we would reduce the power by 1. You'll notice I've just kept this the same. I've ignored the fact that there is a function here, and I've just treated it as if it were just x to the power of a half. That is what our outside function is doing. It's just raising something to the power of a half. So I've multiplied by the power, and I've reduced the power by 1, and I've just ignored that there's this function here. The way we're dealing with that function is we've differentiated it over here. So if I tidy this up, we get 3 halves times 3x minus 5 to the power of a negative a half, which is the same as what we got using the other method. We'd move this down to the denominator and we would square root it. Okay, so we arrive at the same answer. This method, if you feel happy with it and you become more confident with it, is quicker than this method. This is much more methodical though. You're clearly setting out, there's clear stages of what you're doing, and yeah, it's clear to see what's going on here. So both methods work, obviously. Both methods will give you the same answer. The method in blue is slightly quicker. The method in black is absolutely fine as well. The formula for the method in black is in the formula guide. The formula for the method in blue is not. So it's your choice as to which you use.